The intersection of nested intervals is always non-void.
Like monotonic.
Just nested. You know, one interval inside the other.
Yeah, I guess I'm 11.
Well,
It's not minus 1, minus 0.
maybe.
Well, what if you've got a interval with a discontinuity and all your nested intervals are centered around the discontinuity?
Intervals can't have this kind of, that's what makes the intervals. Okay. Sure. How about 0, 1 over n? Being a typical interval, I sub n, defined to be that. So I n plus 1 is certainly contained in I n, right? That'd be 0 from 0 to 1 over n plus 1, smaller than 1 over n, so it would be inside. So they're nested, right? So what's this? Who's in there? Who's in there? Anybody? Nobody.
Well, he does.
Why is nobody there? 0's in there, isn't it?
No, it's 3. Well,
It's not in there. Oh, sorry. You pick a number. Epsilon. Claim it's in there. I will say to you. Pick n so that 1 over n is smaller than epsilon. And then epsilon wouldn't be in that particular I sub n, then it wouldn't survive any infinite intersection. So this thing is void. So how do you change 46 to make it true? The intersection of nested closed intervals is always non-void. Do they have to be bounded?
Yeah. Yeah, because the point's unique.
Well, there's no claim. No, I see what you're adding a norm of the length going to 0 to get the single point. What if this is here? These are nested.
and to infinity. Do the same thing.
How about 1? How about this? Minus 1 minus n, comma 1 plus n. That's Jn. Are the Jn's nested? Sort of going the other way, aren't they? They're going the other way. Yeah. When n is 1, this is minus. I think this interval is in every one of them. But if the length is going to 0, then they have to be nested the other way. They can't be blown up. They have to be going down. And there can't be any meat in them like this. You know, there can't be some fixed thing. This is like the mouse going through the snake, right? I mean, this is a lump here. If the norm is progressively going towards 0, they have to be nested the other way. And then if they're closed, the nested interval theorem, which is in a more general context known as Cantor's intersection theorem, says that there's a unique point that's common to them all. It's non-void. Okay.
Wait, before we leave that topic, how about a set, let's call it A sub n equals interval n through infinity?
Closed or open?
Closed. take the intersection from N1 to 2, from all those.
Yeah, that's a problem. It's a problem. If you cut this off up here, it would still be a problem. They have to be nested the other way. The norm has to go to 0. That's the intent. Yeah, in any statement of the nested interval theorem or the Cantor intersection theorem, the diameter of the sets as n goes up goes down. So you can't have stuff like this. And that's a good example.
So 46 is false? No, 45.
No, that's the Eudoxian axis. 46 is false.
And you said you can correct it with close.
Yeah, close, and then the norm has to, of the intervals has to go to 0. That's the intersection. That's the one we proved in class. A bounded infinite set of reals always has a limit point.
Yes.
That's the Bolzano-Weierstrass. Yeah, that's true. The limit point could be in or out. If it's BW compact, it's in. If it's closed, it's in. Otherwise, it might be out. You know, 0, 1 is a bounded infinite set of reals. It has a limit point at 0, it has a limit point at 1. Neither one of those is in there. If it contained all its limit points, it would be closed, and then be closed and bounded and be compact. So that's true, but may or may not be in the set.